Welcome to the another session in Frontiers in CFD. So today's objective is to study the heat generation per unit volume and the CFD simulation of lithium-ion battery pack with the 24 cells. So to understand the heat generated per unit volume, we are going to use the source term in the cell zone condition, and based upon that we are going to put the values. In the most of our earlier videos we had the temperature as one of the parameter, or we have considered the heat flux as a parameter, but at the same time you can have the heat generated per unit volume that can be specified as source term in cell zone condition. That will you will see in the upcoming portion of this video. What we need to do is we need to prepare a 3D computational domain. So we are going to follow a research paper, and based upon that we are going to generate a mesh. Definitely we are going to generate a mesh which will require comparatively less time for the visualizing the result, and last thing is to apply the boundary conditions and visualizing the results. So these are the specifications that we are going to follow. Density is 2722 kg per meter cube, specific heat 1200 joules per kg Kelvin, thermal conductivity 0.2, diameter of cell 18, length of the cell is 65, the heat generation per unit volume we are taking as 48750. So this is based upon the research paper which we have. So this is all the images which we are taken as a reference and from one of the research paper. So we are actually not interested in the casing point of view, so we are subtracting that portion of the thickness of casing, and accordingly we are going to prepare the geometry which is related to the fluid zone only, and accordingly we will proceed for the CFD simulation. So the dimensions 130, 90 and 70. So if you see the clear cut view of these three images which we have, so 130 and it includes the 4 as a thickness. Similarly on the right hand side image also the 90 includes the 4 thickness, as well as the 70 also includes the 4 thickness and 4 mm as thickness, and based upon that say 9 is there, then so you have to consider that 4, and so you have to subtract the 4 while you are generating the geometry for the fluid pack. So these things are taken into consideration while we can say preparing the geometry, and later on in subsequent we can say while preparation of geometry we'll also come to know this thing. So carefully we have to proceed, like if it's 12.5, so we need to subtract that 4, and accordingly things will proceed for us. The workbench window, so click on fluid flow fluent. So here, so new design modular geometry. So we need to understand what we are going to do. So we are not considering the casing portion over here, so we'll be just considering the internal portion of that, and based upon that we are going to we can say simulate this. So if I consider that there will be this total is 90, so 90 minus 8 it will be 82, and on this side it will be 130 minus 8, that is 122. So accordingly our dimensions will be 122 by 82. So let's go with select the units, millimeter. So create a primitive, let us say cylinder, sorry, not a cylinder, I will start over. So first of all set the units to millimeter. So create, let's say, box here. Now what should be the dimension of box? We should follow this okay, so it should be 122 by 82. So let's make the geometry of box. This is 122 by z component will be 82. So this will be your 65, so I will keep it as it is as the dimensions of battery pack, and let's make it generate. So make it add to frozen, and let's make it generate. So this is how the first thing which we have prepared. The height we have took as a 65, and accordingly we are going to proceed and draw one by one cell. So right now what you are observing is the top view of an object, so accordingly we'll try to proceed. So this is 15, and sorry, this is first distance is 11, and this is 11. So 11 11 we will prepare a cylindrical. So create a kind of cylinder at a make it add to frozen. So select radius that is equal to so I will put it 9.5. So this is make it 65. Let's make it 0. So why we took it 95 9.5? Because we are considering the cylinder of diameter 18. Along with that we are considering a casing of thickness 0.5 mm on both sides. So based upon that we are putting it 9.5. So 9.5 multiplied by 2, it will be 19. So 1 mm will be a thickness that is 0.5 on the either side. So based upon that we are going to proceed. So this is 11 and this is your z component is 11. So let's make it slice and let's make it generate. So this is the first cell that we have generated of radius 9.5 over here. So similarly we have to generate the remaining one. So the other one will be at a distance of 31 by 11. So let's one more time create primitive cylinder. So x will be 31 and this will be 11 as it is. This will be 65, this will be 0, and make, instead of add material I will make it slice material and generate. So you will be having a second one which has been generated. Similarly one more material we can slice. So this z component will be 11 as it is, this will be your 65, this will be equal to 0, and let's check the dimensions. So that will be 51. So let's make the x component to be equal to 51. So let's make it generate. So one more time let's go for create primitive, let's say cylinder and slice material. This will be 11 as it is. Here it will be I think 71. So put this is 71, this will be 65, this will be equal to 0, and let's make it generate. So we have very small clearance in between, so you can actually have a different value also. So let's go to the one more time cylinder, instead of make it frozen, this will be 11 as it is, this will be 65, this will make it 0, and x component I will take as again this will be 91. So we'll put here x component as 91 and let's make it slice material and generate. So one more time create primitive, let us say cylinder, instead of add material make it slice material. This will be 11 as it is, this will be 0, and now it will be 111. So make this as a 65, this make it 0, and let's make it generate. So this is how the objects are being generated here. So similarly we required cylinders, make it slice material. Now x component will be 11 as it is, but here it will be the first one, that is 31. So put here is 31, this will be equal to 65, this will make is equal to 0, and let's make it generate. So second one we are generated. Similarly go to this next, instead of add material make it slice material, x component will be 31, z component will be 31, make this as 65, make this equal to 0. So let's make it generate. So create primitive, that is cylinder, instead of add material make it slice material, z component will be 31 as it is, so this will be your 51, this will be 65, this will make is equal to 0, like that. So make it generate. So one more time create a primitive, that is cylinder. So this will be 31 over here, this will be 71, this will be 65 and 0. So instead of add material make it slice material and generate. So one more time create primitive, that is cylinder, instead of add material make it slice material, x component will be equal to okay 71 we already used, so let us say 91, this will be 31 as it is, this will be 65, this will be equal to 0. So instead of add material make it slice material. One more time let's take primitive, that is cylinder, make it slice. So this will be 111, this will be equal to 31 again, so make it 65, this will make equal to 0. So let's generate. So we are generated for the two rows. Similarly we'll do it for the remaining. So one more time, instead of add material make it slice material, x coordinate now will be equal to 11 first, this will be equal to 51 now, make it this one 65, let's make it equal to 0, and let's make it generate. So third one we are approaching. So one more time make it cylinder, instead of add material make it slice material. So this will be again 31, available here. This will be your 51, so make it 65 here, and remaining component will be equal to 0. So let's make it generate. So we have generated here. Similarly, one more time, let's click cancel this. So one more time, click primitive, that is cylinder. So this make it slice material. X component now will be equal to your 51. This will be equal to 51, so it will be somewhere here. Make it 65. Let's make it 0. So let's make it generate. So one more time, click on the primitive, that is cylinder. Instead of add material, make it slice material. X component will be 71 now. This will be 51 as it is. Make this is equal to 65. Let's make it 0. Let's make it generate. So here we have, so one more time, let's create primitive, that is cylinder. Instead of add material, make it slice material. X component will be equal to 71 now. This will be 51 here. So let's make it 91. We already taken this. So this is 65. Let's make this equal to 0. So let's have it on the other side. One more time, let's create a primitive, that is cylinder. Instead of add material, make it slice material. X component will be here 111 then Z component will be equal to 51 here. Make Y component is 65, Z component to be equal to 0. Instead of add material, make it slice material. So one more time, create a primitive. Let's make it slice material. X component will be 71. Z component, X component will be 11. Z component will be 71. This Y component will be 65. Make this equal to 0. And let's make it generate. So one more time, click primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be equal to 31. This Z component will be equal to 71 now. Make this is 65. Let's make it equal to 0. And let's make it generate. So similarly, create one more time primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be 51. Z component will be 71. This will be equal to 65. This makes to be equal to 0. So let's make it generate. So we have done the third one. So one more time, take it cylinder. Instead of add metal, make it slice metal. X component will be equal to 71. Make this is to be equal to 51. Make this also 71. This will be equal to 65. And let's make this equal to 0. So let's generate. So one more time, let's go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be equal to 91 here, 91 here. This will be 71 as it is. Then this will be 65. This will make equal to 0. And let's make it generate. So one more time, create a primitive, that is cylinder. Instead of add metal, make it slice metal. Put X component to be equal to 111, and this is to be equal to 71 here. Make this is equal to 65, and let's make this equal to 0. So instead of add metal, make it slice metal and generate. So we have generated this. Just check it for at any portion we have mentioned by mistake as the slice material or not, so that we can check. Now this is how the pack which has been prepared. Now it's time to put the fluid in we need to specify this as a fluid. So this will I'll make as a fluid here itself, or you can rename this as, let us say, pack. So the dimension, the distance between the cells is quite less over here, so accordingly we can say you can change these values also depending on your configuration. So now next thing is we have prepared the casing. Now I need to prepare the cell. So let's go to the create. I go with the primitive, that is cylinder. So here again, X component I will take it 11. This Z component I will take it 11. Now instead of the earlier radius, that is we can say 9.5 output radius is equal to 9, and let's one more time make it the similar procedure of slice metal. So what you have actually a casing which has been provided here, so that will be useful for if we are considering some other fluid which are in contact, so in that case it will be useful for us. So go for the similar operations which we have done. Instead of add metal, make it slice metal. Now let's take it, this is to be 31, this is to be 11 as it is, make it 65. Let's make the other component to be equal to 0, and let's make it generate. So this is second. Let's go to the primitive. Let us say cylinder. Instead of add metal, make it slice metal. Let's take it 51, let's take it 11, make this equal to 65, and let's make this equal to 0. So let's make it generate. Create primitive, that is a cylinder. Instead of add metal, make it slice metal. Let's take it 71, let's take it 11, make this is equal to 65, let's make it 0, and let's generate. So one more time, create a cylinder. Instead of add metal, make it slice metal. Take it 91, this will be equal to 11, this much will be 65. Let's make this equal to 0 and generate. So one more time, do this is, instead of add metal, make it slice metal. This will be 111, this will be 11, make it 65, and this will be equal to 0. So let's make it generate. So similarly you have to do for all. So let's slice metal. Now x component will be equal to 11 again, z component will be 31, this will be 65. Let's make this equal to 0 and generate. So primitive cylinder, instead of add metal, make it slice metal. X component will be 31 now, z component will be 31, this will be 65, this will make equal to 0, and let's make it generate. So one more time, create primitive, that is cylinder. Instead of add metal, make it slice metal. Make x component to be equal to 51, z component to be equal to 31. Let's make this as 65, let's make this is equal to 0, and let's generate. So one more time, create a primitive, that is cylinder. Instead of add metal, make it slice metal. Now let's take it 91 here, sorry 71 here, then this is 31, let's make this as a 65, let's make this equal to 0, and let's make it generate. So one more time, create a primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be 91, z component will be equal to 31, this will be 65, let's make this equal to 0. So ensure that in each and every case we are having operation that is slice metal. So one more time, instead of add metal, make it slice metal. X component will be 111, this will be equal to 31, this will be 65, and let's make the z component to be equal to 0. So let's make it this is. So one more time, create a primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be taken as 11 first, this will be 71, this will be 65, and this will be equal to 0. So let's make it, sorry, I will put it 51 here, we are doing for the third. And make it generate. So one more time, create a primitive, that is cylinder. Instead of add metal, make it slice metal. X coordinate will be 31, z coordinate will be 51, make it 65 here, and let's make it 0. So this is the second. One more time, go to the primitive, that is cylinder. Instead of add metal, make it slice metal. X component will be equal to 31, this z component will be equal to 51, make this is 65, and let's make it 0. Sorry, this is this component will be 51, and make it generate. So similarly, let's have cylinder. Instead of add metal, make it slice metal. X component will be 71 now, this will be 51 here, this will be 65, and let's make this equal to 0. So let's make it generate one more time. Primitive, that is cylinder, instead of add material make it slice material. X component will take it 91, this will be equal to 51, this is 65, and let's make it this is equal to 0. So let's generate. Let's go for the last part. For this row, let's make it slice material. X component will be 111, Z component will be 51. Let's make this is equal to 65. Let's make this equal to 0, and let's generate. So similarly go for the last. So instead of add material make it slice material. So X component will be now equal to 7, sorry, this will be 11, Z component will be 71, make it 65, and let's make this equal to 0, and let's generate. So one more time, create a primitive, that is cylinder, instead of add material make it slice material. X component will be 14, sorry, X component will be 31, Z component will be 71. Let's make this is 65, and let's make this equal to 0. So let's generate. One more time, create a primitive, that is cylinder, instead of add material make it slice material. X coordinate will be 51, this will be 71 here, and make it 65. Let's make it 0, and let's generate. So one more time, create a primitive, that is cylinder, material will make it X component will be 71, Z component will also be 71, make it 65, and let's take it 0. So let's generate. So one more time, let's make it cylinder, instead of add material make it slice material. X coordinate will be 91, Z coordinate will be 71, this will be 65, and let's make it equal to 0. So it will be generated. So one more time, add cylinder, make it slice material, 111, this will be 71, this will be 65, and this will be equal to 0. So we are done with the all. So as far as this sail and casing is been concerned, we are done with this. Now it's time to go for preparing the inlet and the outlet. Just like in this diagram, you are observing the inlet holes, and here we are observing the outlet fan. So we'll be preparing one outlet and this n number of inlets over here as per the diagram. Now we are generating the inlet holes. So how it has been generated? So this is one cylinder which has been drawn at a distance of 5, and this is 12.5 which has been taken. So we are going to make use of pattern command rather than using any other thing over here. Now if you see the diagram over here, so the total is 90. So out of that we have the thickness that is 4, so that also we need to take into consideration. So from one end the distance that is equal to 5, and similarly here also there will be some space of 4, and then exactly distance will be same, will be on this side also if you are considering the 70. So we have to subtract that particular distance related to the casing also, that is here, that will be equal to 2.5 and 2.5. So this height of the cell will be 65. So if you take this is 22.5 and 2.5 here, and remaining will be 65. So based upon that we say the distance we have to take. So here we are going to follow the pattern option just like the one which has been used here. So one more time, click on patterns, make it select, make it generate. So we have make change over here. Instead of 12.5 I put it 10, so that it will be equally distributed above and below. So this is how we can say the inlet which has been prepared over here. Similarly we'll prepare outlet at the other end. So again we need to go for the other face. So one more time create a primitive, that is cylinder here. So this is right now it is happening here. We want a diameter that is equal to 50, so I will take radius equal to 50. Y component we will need this at the center. So if I consider the total distance, that is say vertically it is 72 minus 8, that is 62. So 62 half if I take, it will be in y direction, so that will I will put is 31 here. And similarly I need this to be in z direction. Orientation should be not in the z direction. I want the orientation to be in x direction, so I will put it 0 z component. And at what distance I want to shift? I want to shift it a distance on this line. So total was 90 distance, out of which we have 82 will be there, so I put it here 82. So you will see just a minute. So the distance is 130, sorry. So I have to put this equal to 130 here, x component, so it will be on the 122, yeah, 122, subtracting 8 the distance. So I need to take this had to be at the center, so let's shift it in z direction. So z is yours here, is z is yours 90. So let's take it 45. Z component is 45, so it will be somewhere here. Let's check if it is at the center exactly or not. Let's make it generate. Instead of add metal, make it frozen, and let's generate it on the other side. So let's ensure this is at the center or not. If it is not there, so accordingly we have to manage. So uh, total is your 82, so 82 will be your 41. So this will be at the center. So right now we have generated this to be at the center. Similarly the y component which we are having, so this is total distance is 65, so this will be 32.5. make it here and generate. So this will be exactly at the center. So accordingly we have made some modifications, slight changes what we have observed. So let's make it generate. Now we need to make this body as a unite. So for this I select so we'll make this as a new boolean operation. So make it apply and generate it. So what we'll have, this will be a single body which has been available. One it is inlet and second is outlet. So here this is your pack, then just casing. So one more time we'll do the casing also first. So second, this is third, fourth, fifth, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, like this. So select all casings here and we'll make them as a part. So make it form new part. Then remaining things which we have to go, the cells, first, second, third, fourth, fifth, and so on. So select all the cells, so make it form new part. So here write as cell, make this as casing, so copy this, ensure that all of them are solid. Okay, say same way, whatever cell we have, so we need to denote that also, so make it cell for each and every name so as to avoid any kind of issues while applying the boundary conditions. So make it here, so make it cell here. Convert each and every to cell. This is just for naming because it will be helpful us to understand and apply the boundary condition. That's why it is important to do this thing. So make it cell and lastly make it cell. So we have done it for each and everything. Cell we have done it for casing, and then this last one is for your pack. Now the geometry part is over. We need to actually proceed with the next part. So the pack should be fluid, we have done that. Casing, it should be metal one, and cell should also be a solid one. So now let's save the work and we'll proceed. So click on save, go to the this PC, yeah, save with whatever folder you are considering. So let's say 24 cell heat generation per unit volume, CFD simulation. So 24 cell heat generation per unit volume, CFD simulation. So we are saving this work. Always it is important to save the work so as to use it later on. So let's go to the meshing part. If the things are done, you can actually close the design modeler window. So let's close the design modeler and let's open with the meshing part. So first thing is to generate the default mesh. Here we'll generate the default mesh. Let's see how it is. So as per the statistics, 1,27,521. I will definitely want to modify this. Let us say 0.002, and let's make it generate. So if it is too much number of nodes and element, then there are chances that the system becomes slow. So depending on the configuration of your computer, you can actually select the suitable element size. So this looks to be okay. 2,29, sorry, 2,94,241. This can also be further reduced. So that depends again depending on your configuration of your computer. So accordingly, you can actually proceed. But I am going to keep this as it is, so as to reduce the time required for the simulation. So now it's time to select all this ends. So I will denote this as an inlet. So select all of them. So carefully you need to select, because we are interested in only the faces. So make it all inlet. And you have to do the name selection here. Okay, so go to the create name selection. I will specify this as inlet. Sorry. Yeah, similarly, whatever we have on the other side, I will say this will be your create name selection as outlet. So these are the two things. Then we have the geometry. Let's visualize the geometry again. So we have three things. One, pack casing. So I hide all other bodies so as to select the casing part. So I am going to apply the convection over here. So that's why it is important for me to select the casing. So I am selecting all the outer faces of the casing. So one more time. So I will put it casing convection. Okay, so I have done the casing convection. Make show all bodies. So now go to the cell, hide all other bodies. So similarly, now specify the cell name selection over here. So create name selection. So I will put it cell boundary. So we have 4: inlet, outlet, casing, convection, and cell boundary. So let's make it update. Okay, once when you are making it, make it all show bodies, and then preferably do for the updates. So let's make it update. We have specified inlet, outlet, then casing, convection, and we have selected the cell boundary. So we are done with the most of the part. Now it's time to proceed with the next part. Let's close the meshing part. So let's go with the setup part. Go to the edit, make it, let us say, around 16. I put it depending on your configuration, so you can select the required one. So I selected 16. So we are going to follow some of the properties. So it will take some time to load. Yeah, so select transient. I put it gravity, let us say minus 9.81. Make it okay. So go to the models, energy equation, I will turn it on, make it okay. Viscous K epsilon, I put it K epsilon, enhance wall treatment, thermal effect, and curvature correction, make it okay. Then I will go with the material. So by default we are considering the air as working fluid, so I'm going to keep this one. In addition to that, I'm going to have the solid material, that is aluminum. So first material I will put it, let us say lithium battery, and I will specify, let us say Li battery. So specify the densities point what we have considered here. So we are considering 2722. Let's put 2722. Then 1200. Let's put it 1200, and have this is to be around zero point 0.2 watt per meter Kelvin. So make it here, and last one is okay. So make it change grade, make it apply, and it close. So one more time I will add one more solid material, that is aluminum as a casing. Close, close. So air, aluminum casing. This is all about material. Now cell zone condition. So casing, ensure that it is solid. So we want this to be of aluminum, so select the aluminum, make it apply, and then close. Then cell we want of lithium ion, that is correct. We need to add source term. Now what source term which we are considering, number of energy. So I will make it constant here, and I will put the value as per the words 48750. So I will put it 48750. Sorry, 48750 as heat generation per unit volume. So make it apply and then close. Ensure that pack which you have selected is by default air. If you use some different material, in that case you have to drag this option and so check suitable wherever whichever is required. So this is cell zone conditions. Let's go to the boundary conditions. Make this as a zone type, so that I put some values as inlet. You can actually put mass flow rate or something. I will put velocity here as 1 meter per second. Make it apply and then close. Then I will not do anything with the casing convection here, but I will just go with the wall casing part here. So in the wall casing I will put the aluminum, and convectivity transfer coefficient, let us say, is equal to 5. Make it apply and then close. So here in cell you have to ensure that it is lithium ion by default, the material which has been specified over here. So let's go to the report definition, make it here, go to the create surface area weighted average, and here take it temperature, select the total temperature. So where I want this to be at outlet, so click on the outlet, print to the console. So here I rename as outlet temperature. So make it okay. So one more time, surface report area weighted average, here temperature, here will be total temperature, and I want it for whole system, so I will put it total temperature at all places. So make it okay. So this is done. Now you can go to the initialization option available. So compute from, you may specify this is to inlet here, and then click on initialize option available. Now once this is done, click on autosave. Let's put it 20. Go to the solution animation, what animation you require. Let's say contours, I need temperature. Here I need total temperature at what I want it at all places. Say first one I put it all, make it save display, then close, select contour, and you may actually give the say total temperature animation, make it okay. So one more, if you want to set, you can click on animation, click on new object, temperature. I just want it for cell, so I put it wall cell. In addition to that, I will put cell boundary contact region TRG, so I will select all this TRG regions. Make it float, make it apply, close, make it save display, close, select contour 2. So I will put it as cell, rename as cell animation. Okay, it is already there, so make it okay. Go to the run calculations, put the value. Let us say I initially start with 10, and let's click on calculate. So we might have to run this for a long time in order to visualize how things are changing. So we'll see first residual, that will show the iterations. Next window, subsequent windows will see the temperature at outlet, temperature at all places. Then animation windows will see one is the total temperature and second one is the temperature of the cells. So we have basically use air as a working fluid. So for this air, we can visualize the inlet to outlet contours. We can also use water as a working fluid because we already has a casing which has been provided. The similar arrangement can be done with the help of water also, and the results can also be checked. So let's just wait for the iterations to complete. So we took air as a working fluid, and and you can see temperature variation. This has to be run for longer time in order to visualize the things. So let's run it for further 100, that is 90 time steps, and just check how things comes at the end of the 100 time steps. are at the end of the time steps, that is around 100 time steps we are performed. So the temperature has reached to around 301.47 Kelvin, and if you see the cell temperatures also, they are visualized, and you can actually have the visualization of contours. Make it okay and just visualize the outlet temperature, and this is your total temperature at all points. So you can actually visualize in top view also. So this is your x direction, and we can visualize how the temperature distribution has been taking place. So this is done for around 100 time steps. So let's save the work and just visualize the things which are in the post process, that is in the result section. Make it click. We need to visualize the contours of temperature, so we'll put the volume rendering here option. Make it volume rendering, take it temperature here. I will put it local. This value you can put as higher. Let's take it 200. It will take some time because of the higher resolution. So we'll have to wait. So let's visualize it in the top view. So this is your x direction. So you can observe the variations in the temperature. As of now we are just around 100 time steps, so we will not see much of the variations, but still you can visualize the temperature here and variations. So if you want, you can see the legends. I will put it to fixed and make it values to be more. Let's say 11. Let's pick it to be higher value. Let's make it to, let's say 0.06. Make it left, center, make it apply. So this is what we are running for 100 time steps. If you want to visualize the temperature streamline, that can also be visualized. So let's take it from inlet color. You need to select variable. Instead of velocity I will put it temperature. Let's make it local and go to the geometry here. Number of points I will put it 100 and make it apply. So we'll see the velocity points also, that will indicates how the streamline is actually moving. So you may need more points, so let's put it around 500 and just visualize the particles. So this is the individual particles you can see. So we don't have much space available here, and so if you click on this, so likewise things can be there. So let's save the work, and this is how the results are to be generated. So at the end of 400 time steps and the flow time of 400 seconds, we observe the temperature that reaches to around 305.62, and say temperature at outlet around, temperature at all and then outlet is around 302. So this is how the variation that can be observed. Now let us try this same simulation with the help of water as a working fluid. So I will save the work, go to the workbench window, so click on this, make it So this is how it is at the end of 400 time steps. At different points we can visualize the different temperatures which have been available. So this is what we have done it for air as a working fluid. So let's do it for water as a working fluid and just check how things are varying. So let's close the CFD post. Yeah, go back to workbench window, save the work, close the CFD post, go to this one more time. Let's close this, save the work. Once this is saved, you click on save as option. Let's say save as. So first we tried with the so next folder I will prepare. Let us say water as working fluid. So the procedure is quite same. So 24 cell heat generation per unit volume for water. So it will take some time for saving and we can visualize the result for the water. So what thing has to be changed, that I will just show you once this is saved. So we'll wait for some time till this has been saved. So work has been saved, you can see water. So just go to the solution here and I need to change the working fluid. Earlier we use air as a working fluid, now we'll use the water liquid as a working fluid. So what thing we have to change, we just have to go to the material section. So in earlier case we run it for 400 seconds and here also we'll try to run it for around 400 seconds and accordingly we'll visualize the things. Okay, so once the loading is completed, go to the material section. Okay, go to the material section here. So I will add material here from this, let us say water liquid, make it copy and then close, make it close. So we have water liquid which has been available. Go to the cell zone condition. So for pack I will select here. Now instead of air I will select water. That's the only thing we have to change. And just go and close. One more time, just check it. Pack H2 water liquid, apply. Then make it close. Go to the initialization. I'm not going to change any other value. So make it say again inlet and click on initialize. So make it here. Once this is loading is completed, click on this and just go to the run calculation and let us run it for first 100 second, 100 flow time and just visualize the things. So iteration will start again from 0 because we have initialize it again. So there will be separate folder which we have saved because we want to first one do with air and second one we are doing with the water as a working fluid. So iterations will again start from 0. As you can see, residual it starts from 0 here. So the similar windows which we had earlier, they will be visible in the same we can say iterations which you are performing, that is temperature at outlet, temperature of all overall system, then animation which we have set, the total temperature, contours of total temperature, and the cell. We haven't changed any other boundary condition, only we have changed in the cell zone condition. We have specified, instead of air, we have specified the water as a working fluid. So we'll wait and we'll check what will happen at the end of, say, around 100 time steps. So we have performed around 400 time steps. Earlier for air also we have performed the 400 time steps. So at the end of 400 time step, we observed the temperature is around 303, which was far slightly lower than what we use in case of air as a working fluid.